In this video, I will show you how to evaluate a definite integral. Now, up until now, we have been finding the indefinite integral, or antiderivative. So what is this definite integral business? Well, you see these little numbers right here, the 1 and the 3. The 1 is called the lower limit of integration, and the 3 is the upper limit of integration. That's what makes this a definite integral. And I'll show you what to do with those in a minute. But the first step of finding the definite integral is to ignore the numbers and find the antiderivative like you normally would. So term by term, we will use the power rule of integration and increase this exponent by 1. So then we get x to the 4th power. Then we divide by the new exponent, but 4 divided by 4 is 1, so we write nothing. Moving on to the second term. Increasing this power by 1, we get x to the 3rd power. Dividing by the 3rd power, well, 3 divided by 3 is 1, so that's gone. So if this were the indefinite integral, we would go ahead and put a plus c onto this, and this would be our final answer. However, because this is a definite integral, we are not going to do that. Instead, let's put parentheses around this, and here's where the lower limit and the upper limit come in. We're going to put a vertical line right here, and we'll put the lower limit of integration and the upper limit on that little line. So this expression means that we need to evaluate the expression at the upper limit. So we're going to evaluate this expression at 3, and then we're going to subtract the value of the expression at the lower limit. So we're about to do upper limit evaluation minus lower limit evaluation. So starting with the upper limit, this expression will give us 3 to the 4th power minus 3 to the 3rd power. Moving down to the lower limit, this expression will give us 1 to the 4th power minus 1 to the 3rd power. Technically, this is a valid answer to the question. All right, this is just a numerical expression, and this would be perfectly acceptable for a free response question on the AP exam. However, oftentimes you'll see this on a multiple choice question, and it will definitely not be left like this. So let's keep going and simplify further. So 3 to the 4th power, that's going to be 81. All right, so now I've got 81 minus, and then 3 to the 3rd power is 27. Okay, and then minus, and 1 to the 4th power is 1. 1 to the 3rd power is still 1. Okay. Whoa. I meant to put 1 right there. So interestingly, this part right here is just going to give us 0. So that means looking at the first part, we are left with a numerical answer of 54. Okay, so a definite integral like this is going to ultimately lead to a single numerical value. For number 16, again, I'm going to ignore the lower and upper limit of integration at first, and let's just find the antiderivative. So adding 1 to this exponent, which is like adding 3 over 3, I'm going to get x to the 4 over 3 power. But then I must divide by this new exponent. But of course, dividing by 4 over 3 is the same as multiplying by 3 over 4. So just get used to seeing this reciprocal a bunch. But again, instead of putting a plus c on the end of this, we are going to put this vertical line, including our lower limit and upper limit of integration. This tells us to evaluate at the upper limit and then subtract the value at the lower limit. So starting with the upper limit, we are looking at 3/4, 8 to the 4/3 power, and then minus 3/4, negative 8 to the 4/3 power. So again, this is an acceptable answer to a free response question. You could leave it just like this. But just in case we have a multiple choice question to deal with, let's see if we can simplify this any further. Please remember when you have a fractional exponent like this, for example, if I have n to the 4/3 power, always remember that this is in the form power over root. So the 4 is the power and the 3 is the root. So that's why this would be the same as having the cube root of n, all right, because 3 is the root, and then to the 4th power. So I'm going to do that right now. So using that thought, I'm going to have 3/4, and this would be the cube root of 8. All right, so I've got the cube root of 8. And then I've got the 4th power. So look, I know I put the 4 on the inside right here, but it really would be the same if I had this the 4th power on the outside. And I think I'm going to look at it this way because I can do the cube root of 8 very easily. Okay, so I'm going to put my 4 out here. I'm going to come back to this. So meanwhile over here, this would also be the same thing as having the cube root of -8. All right, I've got the cube root of -8, and then all raised to the 4th power. All right, we've got power over root. So now what's going to happen? The cube root of 8 is 2. 2 to the 4th power is 16. So right now I've got 3/4 times 16 minus. Okay, now I've got 3/4 times. The cube root of -8 is -2, but -2 to the 4th power is still positive 16. Interesting. So we have the exact same expression minus itself. So guess what? The final answer is just going to be 0. All right, aren't you glad you didn't leave it like this original garbage that we had at first? Knowing that this whole mess is really just 0, this is a lot more meaningful. For number 20, I think we need to rewrite this one a little bit before we begin to integrate. And before we even do that, please remember that the square root of t is the same as t to the 1/2 power. Keep that in mind as I now distribute. So I'm going to distribute this as I rewrite. So I'm going to have the integral from 0 to 2. But if I do 2 times t to the 1/2 power, that's just, of course, 2t to the 1/2 power. And then minus. When you multiply variable expressions, you add the exponents. So this is like having t to the 1 power. So I'm doing 1 plus 1/2, which is 3/2. So right here I'm going to have t to the 3/2 power and then dt. So in this form, we can integrate by doing each term separately. So let's go ahead and use the power rule of integration and increase this exponent by 1. So in my mind, I'm thinking plus 2/2. So this is going to give me t to the 3/2 power. But then I need to divide by this new power. So I'm going to bring down this 2 for a second. But then when I divide by 3/2, I'm really multiplying by 2/3. All right, I'm multiplying by that reciprocal. So just keep an eye on this for later. Let's come back to that. Now on the next one, I am increasing this power by 1. So I'm adding 2/2. So that's going to be 5/2. So I have t to the 5/2 power. And then I divide by that new exponent, which becomes the reciprocal, which will be 2/5. And ultimately, I am going to have to evaluate using my lower and upper limit of integration. So I'm going to go ahead and put my 0 and my 2 on this. Coming back to here, I don't feel like rewriting the whole thing just for this one small change. So I'm going to do it right now. 2 over 3 times 2 over 1. This is 4 over 3. So let's just go ahead and make that modification. All right, so I've got 4 over 3 going on. So time to evaluate using my limits of integration. So I'm going to evaluate at the upper limit and then subtract the value at the lower limit. So at the upper limit, that's just going to be 4 over 3 times 2 to the 3 over 2 power minus 2/5 times 2 to the 5 over 2 power. So that's the value at the upper limit. Now I'm going to subtract the value at the lower limit. So looking at that 0, I've got 4 over 3 times 0 to the 3 over 2 power minus 2/5 times 0 to the 5 over 2 power. So right here, this is really the answer, but let's simplify this out a little bit. Especially with all of these zeros in here, this first term is just going to be 0, the second term is just going to be 0, so really this entire expression has a value of 0, which does not need to be written. But remember, a fractional exponent is in the form power over root. So this is really the same thing as having 2 to the 3rd power, all right? That's the power. And then the square root of that. And then I have my 4 over 3 in front. And this is the same thing as having 2/5 times the square root of 2 to the 5th power. Now, of course, 2 to the 3rd power is 8. So I have 4 over 3 times the square root of 8 minus 2/5 times the square root of 32, since that's 2 to the 5th power. Simplifying these radicals, we know that 8 is 4 times 2, and 32 is 16 times 2. So we will end up taking the square root of 4 and the square root of 16 and sort of bringing that outside the radical. So we will have 4 over 3 times 2 radical 2 minus 2/5 times 4 radical 2. So if we just multiply right here, we're going to have 8/3 radical 2 minus 8/5 radical 2. Because they both have this radical 2, these are actually like terms. So we need to just go ahead and do 8/3 minus 8/5. And I think I feel like doing that off to the side. So if I have 8/3 minus 8/5, you know that we would get like denominators by multiplying by 5 over 5 over here and 3 over 3 over here. So that's going to give us 40/15 minus 24/15. So a simplified answer would be 16/15 radical 2. And this is what you would likely see on a multiple choice question. Ooh, number 24 involves absolute value. At this stage in the game, I would recommend that we approach absolute value problems graphically. So we know what the parent function for absolute value looks like. It forms like this V shape. So just keep that in the back of your mind. But before we get started, I'd like to rewrite this a little bit. Okay, so we have the integral from 1 to 4. I'm just going to rearrange the order of this to make it more obvious what we're looking at. So we have the absolute value of x minus 3. Well, actually, negative absolute value of x minus 3 plus 3. So we have an absolute value where the parent function is going to be upside down because of the negative sign. It's shifted 3 to the right because of the minus 3, and the vertex will be up 3 because of the plus 3. So let's draw a graph of that over here to the left. So here comes the vertex of my v right here to the right 3 and up 3. And we know because of the -1 in the front that the slope of one side will be -1. It's just going down 1, right 1. All right, which would land here. And the left side will just have a positive slope of 1. So it will look like this. The integral of a function means the area between the curve and the x-axis. So from 0 to 6, the integral of this function would be this area right here, right? The area of this large triangle. However, we have limits of integration. The lower limit is 1 and the upper limit is 4. That means we actually only want the area under the curve between 1 and 4. There are multiple ways to calculate this area, but the one that's sort of jumping out at me is, what if we were to calculate the area of the large triangle first, and then subtract the areas of these two smaller triangles on the left and right? So the area of the large triangle, remember 1/2 base times height, that's the area of a triangle. The base of the large triangle is 6, and the height is 3. So 1/2 6 times 3. There's an expression for the area of the large triangle. Now we can subtract the first small triangle, so minus 1/2 base times height, minus 1/2 1 times 1. Now for the other small triangle on the right hand side, the base is 2 and the height is 2. So we are subtracting the area 1/2 2 times 2. So this is an expression for the yellow area. This is an expression for the definite integral from 1 to 4. So if this were a free response question, you could actually leave your answer like this. But what if it's going to be a multiple choice? So let's keep going and simplify this a little bit more. Let's see, 6 times 3 is 18. 1/2 of 18 is 9. 1 times 1 is 1. Half of 1 is 1/2. 2 times 2 is 4. Half of 4 is 2. 9 minus 2 is 7. And then minus 1/2 is 6.5. So this would be the final answer. Let me just quickly mention that another way we could have done it is that we could have calculated the area of this rectangle and then subtracted these two white triangles. Number 28, as we integrate term by term, the integral of 2 is going to be 2x. The integral of cosine is sine. So we have 2x plus sine x. So here are my limits of integration. So we will evaluate from 0 to pi. Here's where we subtract the value at the upper limit minus the value at the lower limit. So we will have 2 times pi plus sine of pi, that's the value at the upper limit, minus 2 times 0 plus sine of 0, the value at the lower limit. So let's see, sine of pi. Remember that looking at the unit circle, pi is right here. Sine is the y value, so the sine of pi is 0. So this part right here is going to be 0. While we're at it, let's talk about the sine of 0. Well, 0 is right here. The y value here is also 0. So the sine of 0 is 0. So both of these terms are gone. So that leaves us with 2 pi right here. Of course, 2 times 0 is 0. So this whole thing is gone. So really all I have left is 2 pi. So that's the final answer. For this last problem, we need to do a little side lesson. remember that the derivative of tangent is secant squared. And therefore, the integral of secant squared is going to be tangent. Similarly, the derivative of cotangent is negative cosecant squared. Therefore, the integral of cosecant squared is going to be negative cotangent. Let's go ahead and integrate term by term. The integral of 2 is going to give us 2x. But then the integral of cosecant squared, as I just reminded you, is going to be cotangent, well, negative cotangent. That negative is actually going to change this subtraction to addition. So we will have plus cotangent x. And we will evaluate using our lower limit and our upper limit of integration. So let's start with the upper limit. So we have 2 times pi over 2 plus cotangent of pi over 2. And then we must subtract the value at the lower limit. So this will be 2 times pi over 4 plus cotangent of pi over 4. By the way, do not leave your answer like this because we really must evaluate trig functions. But first of all, simplifying this first term right here, these 2's are going to cancel each other out. So that's just going to leave me with pi so far. What about cotangent of pi over 2? Let's sort of think that through off to the side. Pi over 2 is sitting up here at the top of the unit circle. So we want to know what is the cotangent of pi over 2. So your thought process should be cotangent is cosine over sine. And then cosine at pi over 2 is 0, while the sine f of pi over 2 is 1. So that's just going to be 0. So this whole term right here is 0. So far I have pi plus 0. Okay, now pi over 4 times 2, the 2 goes into 4 twice. So that's going to leave me with pi over 2. What about the cotangent of pi over 4? Well, pi over 4 is this sort of 45-degree angle right here. Here's pi over 4. Remember, the cotangent of pi over 4 is going to be cosine over sine. And we know the cosine of pi over 4 is 1, and the sine of pi over 4 is also 1, so the cotangent of pi over 4 is 1. So I'm going to end up with pi over 2 plus 1. So what will all of this simplify down to? Don't forget to distribute this minus sign. We have pi minus pi over 2 minus 1. Pi minus pi over 2. This is like a whole pi minus half of a pi. So that's going to leave half of a pi. So I've got pi over 2, right? This part right here simplifies down to pi over 2. And then we still have the minus 1. So that's as far as we can go. So the final answer would be pi over 2 minus 1.